A small office on a weekday morning. An employee finishes a report, moves the cursor, and clicks print. In that fraction of a second, we cross the threshold from the physical world into the machine. Inside, that document becomes a highly structured pulse of data. But to reach the printer, this data has to navigate a chaotic, tangled web of local network cables and switches. It has to find one specific machine among dozens. Before it can move, the sending computer needs an identity. The network's DHCP server assigns it a dynamic starting IPv4 address, something like 192.168.1.10. This gives our data a point of origin, so it can map a path to the printer's destination address. Without a perfectly rigid, universally understood system to structure those addresses, this simple print job would dissolve instantly into the digital noise of the local network. That rigid structure is built on 32 binary bits. To make these bits readable, the system locks them into 4 distinct blocks of 8, called octets. This is the foundation of the IPv4 address. In the original design, addresses were divided into strict classes. Class A networks claim only the very first octet to identify the network itself. That leaves the remaining 3 octets entirely open for host addresses, creating a massive grid capable of holding over 16 million devices. They were built for the largest organizations on Earth. Our small office network falls into Class C. This reverses the math. It reserves 3 full octets for the network identity, leaving only the final octet for devices. It provides room for exactly 254 hosts, the perfect contained scale for a local business. The remaining ranges serve specialized roles. Class D handles multicast, delivering a single transmission to an entire group of receivers at once. Class E remains locked away, reserved entirely for future experimentation. By embedding the class directly into the first number of the address, the protocol ensures that every entity, from a massive global telecom server to a single laser printer, has a mathematically appropriate scale to exist within. Back in the office wiring closet, an IP address alone still isn't enough to route traffic. The network hardware requires a filter to make sense of the numbers. That filter is the subnet mask. This sequence of ones and zeros mathematically slices the IP address in half. It isolates the network portion from the host portion, separating the broader street from the specific house. That single calculation provides the crucial context. It allows a device to instantly determine if its target is sitting on the same local street, or if the data must be handed off to a gateway router to find it. Once the address is established, the raw print data still cannot travel unprotected. It is encapsulated inside a mandatory 20-byte fixed header. This diagram shows the IPv4 datagram header. Notice the bottom bands. They lock in the 32-bit source and destination addresses, bookending the payload. Higher up, the version field identifies the protocol, while the protocol field signals TCP or UDP. This datagram header functions as a self-contained digital passport. It carries every instruction the network hardware requires to route and deliver the enclosed payload. The network is a labyrinth of physical switches and cables. If an error occurs and a packet gets lost, it could theoretically bounce between routers forever, eventually choking the hardware. To prevent this, the header includes a mechanism called time to live, or TTL. It is a strict hop limit. Every time the packet passes through a router, this counter ticks down by exactly 1. If that counter hits 0 before reaching its destination, the router violently discards the packet. It then fires an ICMP time-exceeded message straight back to the sender. It is a ruthless but necessary self-destruct sequence. It actively protects the global internet from suffocating on ancient, endlessly wandering traffic. Sometimes the data encounters a physical limitation. A pathway might have a smaller maximum transmission unit, a bottleneck the datagram simply cannot squeeze through. When this happens, the router checks the header's "Don't Fragment" flag. If that flag is clear, the router begins slicing the payload into smaller, manageable chunks. Looking back at the header schematic, the router executes this by manipulating the second row. It uses the identification, flags, and fragment offset fields to mathematically map out exactly how these scattered pieces relate to one another. Fragmentation ensures that data can seamlessly cross completely different generations and types of physical hardware without ever dropping the connection. But suppose this payload wasn't a local print job. Suppose it was an external request heading out of the office and into the public internet. Here we hit a boundary problem. Our office device uses a private Class C address. Out on the open internet, that specific number is completely invalid. It is entirely invisible to external servers. The edge router intercepts the packet, replacing the jade green private address with its globally unique sapphire blue public address. When the reply returns to that public address, the router checks its table, restores the private tag, and routes the response to the correct device. This process, network address translation, allowed an entire office to share a single public connection. By drastically reducing the number of globally unique addresses we had to hand out, NAT bought the early internet decades of extra life. Returning to our original print job, the fragmented data reaches the final stretch of local copper wire. Here, the address resolution protocol maps the IP address to the printer's physical MAC address, guiding it over the last inch. The scattered packets finally flood into the printer's network interface card. Immediately, the hardware begins the reassembly math. It reads the identification fields to group the incoming fragments and uses the offset values to snap them back together in perfect sequence. The process only stops when the final More Fragments flag reads 0. Despite being chopped into pieces and fired across varying physical hardware, the payload is restored exactly as it was created. In the physical world, the laser printer quietly whirs to life, pushing out the requested report. The employee retrieves the paper, completely unaware of the vast mathematical undertaking that just executed flawlessly in the blink of an eye. This process of encapsulation, routing, fragmentation, and delivery is happening millions of times simultaneously, radiating outward into the infrastructure of the globe. IPv4 is a silent, highly engineered system of masking and translation. It is the invisible architecture that quietly holds the modern digital world together.